Assalamualaikum and a very good day. My name is Siti Zahra May binti Abdullah and I will present this one article that uses the quality control tool to solve their problem. The case study that I will be presenting is the implementation of statistical process control techniques to reduce the defective ratio by Farag El-Sharif and Hashmat 2018. A little background of this company. The company is involved in manufacturing of cement bag in Egypt. This company ranks among the top producers of cement globally. Cement bags are critical in the cement production cement production industry as they serve the purpose of packaging the cement produced. This ensures that the cement is securely transported and delivered to various locations, maintaining its quality and usability. The introduction part consists of two parts which describe the company's problem. The first problem is the high variability and defective rates, and the second problem is the economic impact towards the company. The high variability and defective rates are because there are a lack of supervision and quality control measures, leading to increased variability in this production process. This resulted in a high number of defective cement bags. Specifically, about 56% of the bags were found to be defective, primarily due to the issues such as mismatching of triangular pockets, hole perforation, and overlapping. The economic impact towards the company is because of the defects in the cement bags resulted in substantial material losses, costing the company approximately $330 per day. This loss was deemed unacceptable by the quality managers, prompting the need for a robust solution to address the quality issues and reduce the defective ratio. The company proposes to use statistical process control (SPC) technique as a method to reduce the defective ratio of their cement bags. There will be 4 specific steps outlined for implementing SPC, include a strategy under Total Quality Management (TQM), identification of the process, identification of key product characteristics, and the SPC tools that are used in this case study. The SPC is a strategy under Total Quality Management (TQM) that involves using statistical method to monitor, control, and improve processes in manufacturing and services. These techniques is used to address the high defect rates in the cement bag manufacturing process. The company experienced substantial losses due to a high number of defective bags. The primary defects were identified in bag dimensions and other quality attributes, leading to the significant material waste and customer dissatisfaction. The company was losing around $330 daily due to defective cement bags. The main defects include mismatching triangular pockets, hole perforation, and overlapping. In this SPC implementation, through the data collection for over 4 months, which is from April to July 2017, data was collected from 2 daily samples of 4 bags each across 2 shifts, morning and midday, for 25 working days per month. This resulted in a total of 6,400 bag samples. The check sheets in the SPC implementation is used for recording data on variables which is bag's length and valve width, and attributes like colors, vent holes, and gluing. The figure shows the cement bag drawing. The drawing is labeled with the matching of triangular pockets, vent hole perforation, and the overlapping ratio of the bags. From the data collected and check sheets for the bag length is collected. This resulted in the average value of the bag length is nearly 59.8 cm, with the CPK is 0.07, meaning that the process center is moved towards the left and contributes in a great extent to process capability to meet the desired specification, and it's imperative to the significant modification to reach the proper quality. The irregular behavior of the semen bag showed 453 samples were out of control for bag length dimension, about 3,624 bags of total 6,400, with ratio of 56% defective. The average value of bag valve is located nearly at 9.498 cm with CPK of 0.22. 302 samples was out of control for valve width dimension, and about 2,416 bags of total 6,400 with ratio of 38% defective. The average value of bag valve is located nearly at 9.515 cm with a CPK of 0.21. 312 samples was out of control for valve. 312 samples was out of control for valve width dimension, and about 2,496 bags of total 6,400 with ratio of 39% defective. Moving on to the next SPC implementation, which is the control charts. X bar and R control charts are used to monitor variable characteristics. P control charts was used for attribute characteristics. This figure shows the X bar and R chart of the bag length. The X bar chart showed that some of the bag length exceeded 60.2 cm, and so many of the bag length is less than 59.8 cm. While for the R data, many of the sample data exceeded 0.955 and only one bag is lower than the 0.07. This is considered out of control data. This figure showed the X bar and R chart of the bag valve. The X bar chart showed that some of the bag valve exceeded 9.7 cm and so many of the bag valve is less than 9.3 cm. While for the R data, many of the sample data exceeded 0.955 and none is lower than 0.07. This is considered out of control data. This figure showed that the X bar and R chart of the another side width. The X bar chart showed that some of the another side width exceeded 9.7 cm and some of the another side width is less than 9.3 cm. While for the R data, there are many samples that exceeded 0.955 and none of it is lower than 0.07. This is also considered out of control data. This figure showed the P control chart of the attributes characteristics. A number of proportion exceeded the upper control limit of 0.4904 and 3 proportion is less than the lower control limit of 0.1417. The next XPC implementation is using Pareto diagram as the quality control tool. This diagram highlighted the most frequent defects contributing to the major of quality issue. The Pareto chart presented in the different types of defect, including the mismatching of the triangular pockets, vent hole perforation, the overlapping ratio of the bag, valve paper gluing, printing, valve side gluing, and other defects. The most frequent defects contributing to the majority of quality issue is the mismatching of triangular pockets, vent hole perforation, and the overlapping ratio of the bags. The next SPC implementation is by using the fishbone diagram as the quality control tool. This diagram is used to identify potential causes of defects for both variable and attribution characteristics. This figure showed the fishbone diagram for bag length. There are 4 possible causes that causes the bag length to defect, which is the man, method, machine, and material. This figure showed the fishbone diagram for the bag valve. There are 4 possible causes that caused by the bag length to defect, which is the man, method, machine, and material. The figure shows the fishbone diagram for the mismatching of triangular pockets and overlapping ratio. There are also 4 possible causes that causes the mismatching of triangular pockets and overlapping ratio. That includes man, method, machine, and material. In conclusion, The case study demonstrates that the application of SPC techniques in a real-world industrial setting, highlighting the importance of systematic data collection and analysis in identifying and addressing quality issues. By implementing SPC, the company was able to gain better control over its production process, reducing defects and improve overall quality. Based on the analysis, recommendations were provided to reduce the defect rates and improve the overall quality of the cement bags. This included significant modification to the process to achieve the desired quality level specification and enhance the process capability. The reference of this case study can be found in this link. Thank you for watching.